How is radioactive dating done? In our last video, we talked about a phenomenon called radioactivity, which is how unstable atoms will emit pieces of themselves to over time become stable. Now we're going to see how this can be used as a dating method to determine the age of samples. First, we need to discuss something that is called a half-life. A half-life is abbreviated as T1 half, and it's a measure of exactly how long it takes for half of a given sample of material to decay. So here's an example. Let's say we start with 100 pounds of uranium. I don't have that much, by the way, in case the feds are watching. After one half-life has passed, we will have 50 pounds of uranium left. Those other 50 pounds haven't just vanished into thin air. They're still there, but they're no longer uranium. Uranium decays into other elements like thorium and eventually into stable forms like lead. After another half-life passes, we will only have 25 pounds of uranium left. And after yet another half-life, we will only have 12.5 pounds. Knowing the half-lives of the isotopes you're working with is fundamental to radiometric dating. But you might be wondering, how do we know the half-lives of these isotopes? Some of them are in the millions or even billions of years. So how could we possibly have ever observed these, right? Humans haven't been around watching atoms decay like that. Well, the answer is that they're bound by mathematical equations, and I'm going to show you how we can derive this just in the present day without making assumptions about the past. So, here's the equation. The natural log of nt over n naught is equal to minus kt. What's going on here? So we've got the natural log of nt. Nt is the amount of radioactive material that we have in the present when we're measuring it. And naught is the amount of radioactive material we had at the beginning before this started decaying. And that's equal to minus k. K is the rate constant, which is specific to the particular isotope, and then t, which is the time elapsed. So we can rearrange this equation to solve for k, the rate constant. Once we have k, we can put it in this equation. T1 half, that being the half-life, is equal to 0.693 over k. In case you're wondering, 0.693 is just the natural log of 2. And so using this, we can determine the half-life. So we can do this just in the present day by taking a specific amount of material and then observing as it decays, and then we can use that to determine k, which we can plug into here to determine the half-life. So let's work through an example now. Let's say that we had a rock specimen in which we're monitoring the decay of uranium. How do we determine how old it is? Let's walk through this. So in a rock specimen, we've got the most common isotope of uranium, uranium-238. We've got 1 gram of that. We've also got something else in our rock, lead-206. Lead-206 is a decay product of uranium. So we also know T1 half, which is the half-life of uranium. It is equal to 5.4 times 10 to the 9th years. 5.4 billion years. So, given this information, how do we determine how old our sample is? We need to begin by determining the rate constant, and we can do this since we are given T1 half. All right, so let's do this. T1 half is equal to the log of 2 over k. Let's rearrange this so that we get k on this side is equal to log of 2 over T1 half. When we work that out, we know that the rate constant for uranium is equal to 1.5 times 10 to the negative 10. All right, so now we're ready to plug our numbers into the integrated rate law to figure out how old this sample is. So we've got t, the time elapsed, is equal to the log of nt over n naught over k, our old friend by now. So how do we determine nt? Well, Nt is the amount of the radioactive isotope that we have in the present, and we measured that. That is 1 gram. What about N0? How do we know how much there was of this uranium-238 before it began to decay? The answer is by looking at the decay products in the rock. Remember, we had lead-206? We had 1 gram of it. So that means we add our 1 gram of lead-206 to our 1 gram of uranium-238 to get 2 grams of uranium-238 in the beginning. Now that's overly simplistic because in reality, there's all sorts of decay products along the chain that we would really need to add up to determine the actual mass. But this is just kind of a simplified version. All right, and then we also have our K, which we just determined to be 1.5 times 10 to the negative 10 years. All right, so now let's just rewrite the equation, substituting these in. The time elapsed is equal to the log of 1/2 over 1.5 times 10 to the negative 10 years. Once we work that out, we get T being equal to 4.5 billion years. And that should be how old our rock sample is. So we made 2 main assumptions here. Firstly, that N0 is not influenced by contamination. That is, that the decay products aren't leaching out of the rock or being forced into the rock by groundwater, heat, or some other phenomena. And secondly, that K remains constant. In our next episode, we're going to discuss the implications of this for young Earth creationism and how creationists have attempted to solve this problem. If you enjoyed this video, please make sure to like and subscribe.